Hi, this is Zach Fulkerson with the Critical Care Curriculum, and today we're going to do our introductory lecture into acid-base. And so we're going to be going over just some basic principles. First, before we get into the meat of this, let's go over quickly normal reference ranges. So the blood pH is normally kept between 7.35 and 7.45. We usually call normal right around 7.4. Anything that's less than that is acidotic. Anything higher than 7.45 is alkalotic. Our partial pressure of carbon dioxide, you also see this called PaCO2 sometimes for partial pressure of carbon dioxide in the artery. That is usually between 35 and 45 millimeters of mercury. The bicarbonate or total carbon dioxide concentration in the blood is in the range of 22 to 26 millimoles per liter, millimolar. You'll also see that in milliequivalents per liter. And finally, the anion gap. This is going to vary between, depending on the lab that you use. It's usually somewhere in the neighborhood of the 12 range, the 10 to 12 range. I've given a fairly broad range of normal anion gap, and you're really going to have to use whatever lab you're using at your institution. All right. Acid base is all about this ion right here, the hydrogen ion, and as it goes up, we call this acidosis or acidemia. And of course, a high hydrogen ion is correlated with a low pH, and anything less than 7.35 is acidosis. Likewise, a low hydrogen ion concentration is a high pH, and it's anything greater than 7.45 is going to be considered alkalemic. All right. There are a number of ways that we keep this hydrogen ion concentration within a very tight range, and the body uses a number of different transporters and buffer systems. The main buffer system that we care about is the one that involves bicarbonate and carbonic acid. There are other buffer systems, including phosphate, including proteins. We don't care about those quite so much because they're not as dynamic in regulating acid-base status as this one is right here. So why is this so dynamic? Because this will split apart into water and carbon dioxide we can quickly expel via the lungs. So this we have a way of getting rid of, and so we have a lot of control over acid-base through this buffer system right here. So this also gives us a good idea of the different types of processes going on. So if there's a derangement going over here, we call that a respiratory acidosis or respiratory alkalosis. And if the problem is happening over here, we tend to call that a metabolic acidosis or metabolic alkalosis. So those are the varieties. There's metabolic acidosis and metabolic alkalosis. The metabolic acidosis, of course, is broken into non-anion gap or normal anion gap, as well as an anion gap or elevated anion gap. This tends to be associated with a high chloride. This tends to be associated with some other organic acids, such as lactates, such as keto acids, such as formic acid from methanol, things like that, that cause an elevated anion gap, which we'll talk about. And then, of course, the other variety is respiratory acidosis and respiratory alkalosis. And each of these vary slightly depending on whether they are acute or chronic. And it's just because the kidneys can take a lot of time to compensate for a respiratory acidosis. So the compensation you get is usually less in acute settings, and it's usually more in chronic settings. All right, let's get back to this equation real quick, and let's talk about our first acid-base disturbance, which is respiratory acidosis. All respiratory acidosis is simply when the lungs are not able to ventilate or not able to expel carbon dioxide at an appropriate rate. So what happens? The carbon dioxide or PCO2 starts to go up, and that drives this entire equation this direction. That causes the formation of carbonic acid, which then breaks apart into bicarbonate, and of course, hydrogen ions, which is what causes the drop in pH or acidosis. In each of these, you're going to see an elevated bicarbonate. That's a buffer system, and it's, of course, produced by this breakdown of carbonic acid. If we etiologies that cause this are COPD, obesity, hypoventilation system, neuromuscular weakness, and of course respiratory suppression via opiates. You're actually going to see the CO2 level rise much more quickly than you'll see the oxygen levels fall in most of these states. It's much more sensitive. This is why in people who are on PCA pumps, that's a patient controlled analgesia, so like a fentanyl drip or Dilaudid drip or something like that, we often will measure an end-tidal CO2 because the CO2 is much more sensitive at measuring respiratory suppression as opposed to oxygen. Now, the way we compensate for this is with the kidneys. So the kidneys can actually get rid of hydrogen ions in the form of ammonium ions. They can also chronically start to reabsorb bicarbonate. So as the respiratory acidosis becomes more chronic, the bicarbonate will go up more and more and more. All right, let's move on to the next thing, which is respiratory alkalosis. So in this particular case, for whatever reason, you are ventilating too much or driving off too much carbon dioxide. That's causing the PCO2 to go down, which is driving this equation more or less this direction. That causes a decrease in bicarb because all of this is getting pulled this direction, and it causes a decrease in the hydrogen ion, which is, of course, an increase in the pH. What are some etiologies of this? Hypoxemia, so someone with, say, a pulmonary embolism or pneumonia may develop a respiratory alkalosis because they have a respiratory drive from their hypoxemia. Cirrhosis can often cause this. And finally, people who are septic can actually develop a respiratory alkalosis. Once again, the change in the bicarbonate is going to be much greater in people who have a chronic respiratory alkalosis than it is in people who have an acute respiratory alkalosis. All right, so those are the respiratory problems. Let's get on to metabolic acidosis, and that's when you have a problem somewhere on this side of the equation, of this chemical equation. This gets a little bit more complicated because there are a number of ways to have abnormalities here. So you could have a problem with losing bicarbonate. So for instance, if you have a patient who is having diarrhea, they might be losing bicarbonate. Or maybe the kidneys have a problem with reabsorbing bicarbonate or have a problem with getting rid of acid. This can be seen in something called a renal tubular acidosis. If you have issues here, that tends to cause a normal gap or a non-gap acidosis. Saline administration will also cause a normal gap acidosis. So what causes an elevated gap acidosis? It is when we're adding some other organic acid. So that organic acid breaks apart into an H plus ion, a hydrogen ion, plus the conjugate base of this acid. So for instance, lactic acid will break apart into hydrogen and lactate, and that will cause an acidosis. That, of course, is manifested by an increase in the hydrogen ion shown here. All of that will tend to drive this equation this direction, right? So if we're producing a lot of hydrogen ion, we're going to push things this direction. And you will initially start to make more carbon dioxide. However, this hydrogen ion is a huge driver of respiration. So a low pH is a massive driver of pH, as is CO2. So because the respiratory drive is so increased, what tends to happen is you tend to blow off more CO2 to pull things this direction to compensate for the acidosis. So in general, we see a low pH, so high hydrogen ion is a low pH, a low bicarbonate, and a low CO2 in a metabolic acidosis. What are some causes of this? Well, if the anion gap is elevated, then it's your classic mud piles mnemonics. So I'm not going to go through everything, but the most common things that we're going to see are lactate and ketoacidosis from diabetic ketoacidosis. Other things that you may potentially see is uremia, that's what the U is, methanol, which gets metabolized into formic acid, salicylic acid. So there are a lot of other things, but the most common thing that you're going to see is lactate and probably ketoacidosis. That's the most common. In terms of a non-anion gap, remember those are problems here. You might have a renal tubular acidosis, which we already talked about. That's when the primary problem is within the kidneys. You may have, say, diarrhea, losing bicarbonate, or you may have actually saline administration, which will also cause a non-anion gap acidosis. So normal saline administration will cause a non-anion gap acidosis. All right, metabolic alkalosis is our final acid-base disturbance we're going to talk about, and that is when we have a drop in the hydrogen ion concentration from either just a loss of hydrogen ions, such as in vomiting, or an increase in bicarbonate. You're going to have resultant respiratory suppression, so the lungs are going to attempt to compensate for this loss of hydrogen ion by shifting things this direction. That's going to cause an increase in the PCO2, so an increase in the carbon dioxide partial pressure. What are things that can cause this? Well, we have vomiting, that's losing hydrogen ions. We have bicarbonate ingestion, so maybe ingesting calcium carbonate, which is Tums, maybe IV bicarbonate administration. Loop diuretics or thiazide diuretics can cause this in adults. And if we're talking about the pediatric population, some genetic conditions such as Bartter or Gittleman syndrome can, of course, cause a metabolic alkalosis. So that does it for the metabolic and respiratory alkalosis and acidoses. What I want to do is I want you to go through each of these processes: metabolic acidosis, alkalosis, respiratory alkalosis, and I want you to select whether the pH is going to be high or low for each of these, if the PCO2 or the PaCO2 will be high or low, and if the bicarbonate concentration will be high or low. Hopefully you got something that looked like this. Of course, with any sort of acidosis, the pH is going to be down, and any sort of alkalosis, the pH is going to be up. With a metabolic acidosis, the primary problem is the bicarbonate concentration is going down, and the CO2 goes down in an effort to compensate. Metabolic alkalosis is just the opposite. And a respiratory acidosis, the primary problem here is the CO2 is too high, and we compensate by raising the bicarbonate concentration. So notice that respiratory acidosis and metabolic alkalosis actually look quite a bit similar to each other, with the exception of the pH. Respiratory alkalosis, just the opposite of respiratory acidosis. That does it for the first talk on acid-base. Next, we're going to be talking about a systematic way that you can go through acid-base problems, because unfortunately, acid-base problems don't happen in isolation. There can be single acid-base problems, double or even triple acid-base problems. It's important to be able to figure these out, because that helps us figure out some of these underlying things that are going on with our patient. So that's going to come up in the next lectures.